So now in this video, we're going to look at these supercapacitors here. So these are interesting supercapacitors. Let's see if I can get the writing. First off, they are polarized. So you charge and discharge these. And this side has to be more negative. You can see a little dash there. This side has to be more positive. You can see a plus there. And they are rated for 5.5 volts right there. And 4 farad. That is both of them. So we looked at that one. This one, it's easier to see the writing. There we go. So 5.5 volts and 4 farad. I don't know that there's any difference between these two. This one's gold, that one's black. And, you know, maybe you'll notice something if you do a bunch more research on differences. Otherwise, I think they're basically the same. So, again, we can charge it to 5.5 volts. You have to charge, and you can use that charge at some point, capacitors. And so what this is saying, the 4 farads there, we can charge it to 5.5 volts. So let's just say we start at 0 volts. If we give this 1 amp of current to charge it, it's going to take 4 seconds. That's what that 4 farad means. 1 amp of charge, 4 seconds to go from 0 volts to 1 volt. And then from 1 volt to 2 volts, 5 seconds. And then 2 volts to 3 volts, 5 seconds. So if we give this a steady 1 amp of current, it's going to take about 25 seconds to go from 0 volts to 5 volts. And that is the current we can get out of it while it discharges. But again, it will go from 5 volts to 4 volts in 4 seconds if we discharge it at 1 amp. So the voltage will change. The current will go down. That is the basic premise of supercapacitors. Now, these also have internal resistance in them, which most supercapacitors do not have. So don't apply every single thing you see in this video to supercapacitors in general. Make sure that they have internal resistance if you're going to be looking at them like I'm going to be looking at them in this video. So now, as I said, their voltage goes up as you put charge into them. Their voltage goes down as you take charge out of them, basically when you're powering something. So we have voltage changes. So an important thing about supercapacitors and capacitors is their voltage at any given time. So we're going to measure the voltage of the capacitor there, and the reason why we're not getting a reading, I have this probe set to the amp setting. So it's a good idea to check where the probes are right there. But in any case, we should still be safe. We had this setting set to a voltage, so probably the meter is just fine. Plus it was in the amp setting. But in any case, let's get that voltage reading. So again, make sure you pay attention to what's going on at all times. So there we can see we got 3.3 volts right there, and the voltage is rising for some reason. I think that's due to the internal resistance. Something going on with that right there. So these are not as simple, it seems, as most supercapacitors. So there's the more negative side. Also the arrows point towards the more negative side. Of course, if you measure this, the arrow pointing to the negative there, if you measure this backwards, you will just get a negative reading. So I'm going to put the red probe to the negative side, the black probe to the positive, and there you can see it looks like about 3.457, and the voltage is holding steady. It's negative because the probes are backwards right there. No big deal. But that tells us a lot. That's how much charge we have in there. It gives us an idea, doing some math, you know, but it gives you some idea what you can power for a period of time with the charge already on here. So these really do not like the chemistry on them going to 0 volts and staying there. They kind of drift back up. So if you have supercapacitors or whatever, you're not sure which side is positive, which side is negative, you can simply measure the voltage. As long as you have a positive number on there, you know you have the probes the right way. This is the more negative side right there, and that is the more positive side. Make sure you wire that into the circuit that way, and usually it'll be indicated though. You won't have to worry about that. So now, we're going to look at how we can use these in a practical circuit. So this can be a simple circuit, of course, but I have the power supply set to 5 volts. There's no current flowing through it right now. First off, the output is off, and so it's not powering the board, but there's no load anyways. And we can look at the voltage. No voltage being applied because there is no load. So what we're going to do, we'll come down here. You can see that we have these two jumpers going across the board. So if I power one side, both sides are powered, and these alligator clips come from this power supply there. So I just clip them to wires and then plug the wires into the board, and it helps to kind of tack them into the board there too, where the alligator clips are, so they don't roam around. But in any case, we're going to take a LED here. So the LED is going to light up when we pass current through it. So the long lead, the anode, we're going to go up one row above this jumper that goes to the negative rail. Short lead, the cathode's going to go to that row where the jumper goes, and we're going to grab the resistor and put that there. So this is a 220 ohm resistor. That's plenty of resistance to protect an LED from 5 volts. Let's zoom back, and I'm going to hit the power button down here to turn the output on. When you see that, the LED turns on, and we can get a pretty good idea how much current's going by hitting that button there. So remember, the 5 volts is less than what these supercapacitors can be charged to. There you can see we powered the LED. As we saw earlier, the supercapacitors have about, I'm going to turn that power supply off, about 3.5 volts or so. Plus, I'm going to disconnect. All I have to do is disconnect that red one, and now this power supply is disconnected. I hit the power button so that we have output going there, but only the negative one is connected, and so no power's reaching the board. Now it's off. I will just completely disconnect it to get that out of the way altogether. So we know that's not influencing it. Now we go down here, and we can take the supercapacitor. It's still a good idea to check polarization, plug that in, and there you can see the LED is lit up. Probably not quite as bright because we're only dealing with about 3.5 volts, but we could charge it higher, of course, or we could plug this one in. We could plug it in the same spot or that spot. So there, we have backup power. These are charged up kind of like a rechargeable battery, but they have some pluses where they don't rely on chemical changes to provide their electricity, just built up charges on both sides. So they won't wear out as fast as a small battery, but they won't store as much energy as a small battery, but they can be used like a mini rechargeable battery. So now we're going to discharge these supercapacitors. So first off, when it comes to supercapacitors, they allow a high amount of current through them. That's why we're dealing with the amp range with the supercapacitors here. You have to limit the current. So of course, in this case, the load limits the current, and I'll plug that in there, and it's limiting the current. That's why it's taken a while for this to discharge. Now I can put this in parallel with that one, plug it in the board for a couple of reasons. First off, they're about the same voltage right there, so they won't really affect each other. Whichever one has the higher voltage will quickly charge the one with the lower voltage until they are equal. So remember, current in, the voltage goes up, current out, the voltage goes down, and so if one has a higher voltage than the other, it will push current into the other one until the voltage is equalized. So it's really safe when they're equal voltages to put them in parallel. One will just charge the other one, the tiny difference that there is. Not a whole lot of current will flow. But these also have internal resistance. So even if there was a large voltage difference between these two, both of them limit current internally. They have internal resistance. That is not true with all supercapacitors, but these particular ones do have them. So assume you don't have internal resistance until you can prove that they do. And hopefully all the ones that look like this do. Now we're going to do another thing you can do with supercapacitors that have internal resistance. We're going to short circuit them out because they have internal resistance. so it's not really short-circuiting a supercapacitor. You never want to short-circuit a supercapacitor, so most of them that don't have internal resistance. This is another reason why it's important to know for sure they have internal resistance. But you're going to see as soon as I go from a positive to negative with the jumper, the LED goes out. And when I release it, it doesn't. So whatever current these can provide, it goes through the wire, and there is no more current available to power the load, because the wire is by far an easier path for the current to flow. And we can pull back here to the multimeter and see. Let's see if we even have yeah, we don't have enough power anymore to power the LED. It is turning on though. These polarized capacitors tend to have some kind of memory. I forget the technical term for it, but when you discharge them and then you release your very low resistance, they tend to build up a voltage again. So when you talk about supercapacitors and capacitors, a lot of it is ideal, and so they don't work ideally. They have some properties that don't make the math work out perfectly all the time, but it's just a general term. So we can look at the voltage that is being provided right now. We saw earlier they were like 3.5 or so. Now it looks like it's about 2.2 in that range. And of course, if I short circuit it, all the current's going to go through the wire, and we're really not going to get much on here. So that's probably the resistance differences from the wire and whatnot bounce around. We probably got a little bit of a voltage divider effect. If I yank this though, now you'll see we have a lot more voltage, and it's rising because of the supercapacitors. As I said before, they're polarized. Their voltage tends to drift back up from where it was before. So now they also have internal resistance, so there's voltage within them that has to go through that resistance. So again, we have that voltage divider effect. So it's limiting current. That current's easily going through the wire. We see no voltage across the wire, even though there's still voltage within the component. So I hope that makes sense. The LED is still starting to glow again each time we do this though, and the longer we would try to fully discharge them, the slower it would take for the voltage to rise back up, and it won't rise back as far. There you can see 1.7. So that's some of the properties of it discharging. Discharging at very low currents, it's going to hold its voltage a lot better than discharging at high currents. As you see there, it tries to stay at its previous voltage as much as it can, but drawing large amounts of current out of it gives you a rapid drop. So now we are going to recharge these. We're going to give them that charge basically I had at the beginning, and probably even more. So I have the power supply set to 5 volts. It's limited to 1.5 amps of current. As I said before, when it comes to supercapacitors, limiting current is very important. Luckily, these have internal resistance. That automatically limits the current. And to begin with, I'm going to unplug these right now. And we're going to apply power to the board. So we could have left them on there, but I want to show that the LEDs right there, we will plug that in there, and then this one to the negative. I'm just going to let the alligator clips remain floating around here. But the power supply limited the current. I'm going to hit the power button. The LED turns on right now. You can see 0.13 amps of current. And when I take this supercapacitor here, so again, I have current limited to no more than 1.5 amps on there, but it has internal resistance. And unfortunately, you can't directly charge supercapacitors with no internal resistance with this, because it doesn't see any resistance. It thinks there's a short circuit, and it cuts the output power. But with these, they have internal resistance. We can power them directly. With this, you're going to see current go up quite a bit right there. And so the reason why I just did that quick, we're also going to take this one and I'm going to try to plug them both into the board at the same time. We saw about 0.25 amps in that range. If I plug both of them, now you see 0.5 amps. So they're charging independently and the LED didn't go out. They're charging. This power supply, we just saw, it needs about 0.5 amps to charge these two up. It's outputting at least, or up to I should say, 1.5 amps. So it can output more than it was needed to charge these and to power the load. As they charge up, as their voltage goes up, you can see that there's less current going in them to charge them. So we got like 4.7 volts there, and that's holding pretty steady because they are charging independently of this load here. So their voltages may kind of shift things a little bit, but for the most part the voltage is being provided by the power supply there. If we had lower resistance in all the wires and stuff, it would be more accurate. But in any case, there you can see they charged up. You can't really tell that right now, but we will unplug the power supply right there, so we can just unplug one or both of them. Right now no current's coming out of them. Probably a good idea to hit that button, turn it off too, also get it off. But now we can look at the voltage that the two of them are providing. So it's about 3.8 volts, but that is because there's a load. There's the voltage divider effect right there. So we unplugged the load and we can go to any 2 points where we come to the rail. There you can see it's about looks like about 3.7 volts that they actually charge to. So looks like we have a ways to go. Let's plug this back in. It does have the 10 ohms of resistance, so it limits current. It takes a little while to charge. So I'm going to turn that on and we'll come back when this gets to about 0 amps of current. It's a good idea to make sure and turn the meter off when you're done using it. So now there's quite a bit less current going in there. That's because their voltage rose up a bit. We got the voltage of the power supply and then the voltage of the capacitors. They have probably about 10 ohms of resistance between those two voltages that limit the current. So it's the voltage difference and the internal resistance. They are connected in parallel, so they're both charging. So effectively this is like an 8 farad capacitor. So you just put them in parallel, it increases the capacitance. So you see if I pluck one, the amount of current goes down in half because it's only charging one right now. So that current that's going in will be the current that we can provide to a load later on. And so more current's charging it right now, there'll be more current available for a load later on. But in any case, you can see here, we have a lot less current here. Current's still trickling in. I've charged these before. It does get down to 0.000 amps, which is the same as 0 microamps, so milliamps I mean. So it does finally get all the way to 0. That's how you know it is fully charged. But I'm going to pluck that out there. It's not charging. Let's take a voltage reading now. So this would be better if we went all the way to 0, but that's going to take time. But there you can see we got a lot more voltage. So they charged up higher and they're going to discharge over time right there. So they have internal leakage and stuff. They don't hold their voltage forever, but they do pretty well. It's going to slow down the voltage drop, plus a little bit of currents going through the meter here and whatnot. But in any case, hopefully that made sense. These are basically rechargeable batteries, and the internal resistance for these particular ones are nice when it comes to safety. There's always a little resistance to limit current, and limiting current is extremely important in electronics. Unfortunately, as we just saw here, they can't charge instantly. This meter wants to be able to provide 1.5 amps of current, and most supercapacitors and capacitors, they accept whatever current you're going to give them. So most supercapacitors would accept that 1.5 amps. Unfortunately though, since they accept it so easily, the meter thinks you have a short circuit and it cuts the output. That's for this meter. So if you're going to charge regular capacitors, you want one where it doesn't shut down automatically. That's not the end of the world for me on this one. And first off, I can just put a small resistance in series with other supercapacitors. But just be aware of that. These limit current, so that's their strength. It's safer. You don't have to worry about too much current in most cases. But you can't charge them instantly. But I don't think these are intended to be charged instantly. I think these are intended for sudden power outages or something. So you are powering, in this case, we are powering this LED right now with the power supply there. So you can see the power, that's the power lighting the LEDs and this unit. But if this unit turns off, maybe you have something that can't lose power for, this may stay lit for an hour or something, 2 hours, who knows. But you may have something that can't turn off suddenly for whatever reason, and it doesn't need a lot of power. You could use a supercapacitor like this pretty nicely, up to 5.5 volts, like that. It'll provide a really low power circuit with power. As you can see there is the two of them. It's not outputting any power, so it's about an 8 farad equivalent. So it's going to take about 1 amp of current about 4 seconds to go down. So 1 milliamp of current should take about 4,000 seconds for one of these, about 8,000 with the two of them, to go from 5 volts to 4 volts. And then another 4,000 seconds from 4 volts to 3 volts. If you go by math. Of course, as we saw before, they tend to like to not drop their voltage when it gets lower, and it tends to not like to stay at 5 volts. But in any case, for the most part, those are general rules, that 1 farad of capacitance takes 1 amp of current 1 second to change 1 volt. So hope that all made sense. It's a really simple component, capacitors in general, but they take a little while to get used to. They are not instinctive. Their voltage changes over time based on current for the most part. There is leakage and other small variables, but the main thing is the current that they're given. Current in raises their voltage over time. Current out lowers their voltage over time. And you can use that to power circuitry there, or you can use it in other ways where you take that voltage change and take effect of that voltage change over time. You may take advantage of that. So in any case, hope that all made sense. I rambled on longer than I should have, but hope you still enjoyed the video. Thanks for watching. Make sure you turn everything off. This you actually have to unplug to fully turn off. The meter is turned off, and I got it off of the current setting. As we saw before, it was still plugged into the 10 amp spot when I started the video. That was not ideal, because measuring current is the easiest way to blow a fuse if you try to measure a power supply directly. So you want to get the plug back to the voltage spot, turn it off, and worst case scenario, leave it in the voltage spot if you're going to take measurements soon. Get it out of that current though. So thanks for watching. See you in the next video.